In this video, we're going to examine average rates of change. And average rates of change have a very simple formula. Okay, they're just slopes of lines, and they are slopes of what are called secant lines. So below here, you can see that we have a secant line. A secant line is nothing more than a line that links 2 points on a graph. And the average rate of change of the function will always be the slope of the secant line on a given interval. So the average rate of change over an interval, in this case, is over the interval a to b, where, usually the x-axis in these contexts represents some quantity like time, and f of x might be position. So you have a change in position over a change in time, and if your position is in terms of feet, then this calculation would have units feet per second. So that would be like a velocity. Okay, so the average rate of change formula often corresponds to some kind of rate, and it would become the average of that quantity. So let's look at a few more examples and how to compute them. Okay, so firstly, you just want to be able to compute the average rate of change of a function. You'll always be given the function, and you'll always be given an interval. So find the average rate of change of f of x equals x squared minus 1 on the interval 1 to 9. So the average rate of change, which I'll just abbreviate as AROC, is going to be, according to our formula, f of 9 minus f of 1 divided by 9 minus 1. Okay, and then you can evaluate the numerator. So f of 9 is 9 squared minus 1, which is 80. F of 1 is 1 squared minus 1, which is 0. And all of that is divided by 9 minus 1, which is 8. And 80 divided by 8 is 10. So the average rate of change is 10. Okay, and just very quickly, graphically, what you're seeing is, if this is the graph of x squared minus 1, looks something like this. Okay, you just found, f of 1 is 0, and f of 9 is 80. This is clearly not drawn to scale, but you found the slope of this line here. Okay, so the slope is equal to 80. Sometimes you're asked to find average rates of change involving a context. So this says find the average velocity of a toy car on the interval 4 to 16, whose position is given by s of t equal to the square root of t. So the average velocity, okay, average velocity is the average rate of change of your position. Okay, so velocity is a rate of change of position. So average velocity is average rate of change of position, and here we've got the position function. So the average velocity is going to be s of 16 minus s of 4 divided by 16 minus 4. S of 16 is the square root of 16, which is 4. S of 4 is the square root of 4, which is 2. And 16 minus 4 is 12. So I get 2 over 12, or 1/6. And again, this has no units, but let's say the time interval was seconds, and let's say that the position was in feet. Then we just subtracted feet. We divided it by seconds, so the quantity here is feet per second. So that corresponds with what we want, right? We're trying to find an average velocity. Here we have a similar question. It's emphasizing the graph itself. It says for the function f of x, find the slope of the secant line between x equals -3 and -1. Well, the slope of the secant line is the average rate of change. Okay, that is the average rate of change. So this is just asking for the average rate of change of the function on the interval -3 to 1. But I'll represent it as slope of secant line. So the slope of the secant line is going to be f of, again, It's like our a and that's our b. F of negative 3 minus f of negative 1 divided by negative 3 minus negative 1. Okay, so I'll let you check on your calculator, but when you plug negative 3 in for f, you end up getting negative 14. When you plug in negative 1, you end up getting negative 8. Over negative 3 minus negative 1 is the same as negative 3 plus 1, so you get negative 2. And then this becomes negative 6 divided by negative 2, which is 3. So the slope of that secant line, which is also the average rate of change of f of x on the interval, is 3. Where this is all heading is a very fundamental idea in calculus, which is the instantaneous rate of change, or the slope of the tangent line. So what you'll notice here is I have the formula for average rate of change again, but I've considered the point point B as a variable. Okay, so that x now is just a stand-in for a variable, meaning we're going to keep a as fixed as some important x value that we care about, and we're going to start moving that x value closer and closer to a, and you should observe what happens to the slopes of those secant lines. They start to approach something. Okay, they have a limiting value, and we're going to explore that numerically in the next couple of examples. So just to get us prepped, notice I have the function f of x equals x squared, and I've got a table of its values, and I've got the point 1, 1, and then I've got a bunch of points that are really, really close to 1, 1. In other words, I've got x values on the left and the right that are really close. What we're going to do is we're going to find the average rates of change between 1, 1 and each of these other points. And a couple things to notice is that, one, those values are going to approach something, one particular number. And then secondly, if you see how that we zoom in on the graph starts to behave like a straight line the closer we zoom into it. Okay, and that's a fundamental idea in calculus, is that functions that often look very curvy behave like a straight line if you zoom in far enough. So we're going to see what this limiting slope is in a second. So right now we're going to compute the average rates of change between the point 1, 1 and all these points that are close to the point 1, 1 on the graph of x squared on the right and left side. So let's start from the left-hand side. So my b is like 0.9 for my first example. So I'm going to find the slope between these 2 points. Okay, so that would be f of, so my x is 0.9, so it's f of 0.9 minus f of 1 divided by 0.9 minus 1, which is the same as, so f of 0.9 is 0.81 according to the table, f of 1 is 1, divided by 0.9 minus 0.1, or sorry, minus 1. And if you do that, you should end up getting the value 1.9. Okay, now let's move the point even closer. Let's find the slope between these 2 points. Okay, 0.99, 0.9801, and 1, 1. So now it's f of 0.99 minus f of 1 divided by 0.99 minus 1. F of 0.99 is 9801 minus 1 divided by 0.99 minus 1. And you end up getting 1.99. And finally, we'll do the closest. So we do f of 0.999 minus f of 1 divided by 0.999 minus 1. And that gives you 0.998001 minus 1 over minus 1. And that ends up being 1.999. So the limit as x approaches 1 from the left-hand side, it looks like that is, if we were to guess, it looks like that should be equal to 2, right? It just seems pretty obvious that those slopes are approaching 2. Let's come from the other side. Now let's do the slope between 1.1, comma 1.21 and 1. So we're doing the right-hand limits now. So that would be f of 1.1 minus f of 1 divided by 1.1 minus 1. But f of 1.1 is 1.21 minus 1 divided by 1.1 minus 1. And if you do that, you should end up getting 2.1. And similarly, we're going to do we're going to do the next point. So that would be the slope between these 2 points. So that's going to be f of 1.01 minus f of 1 divided by 1.01 minus 1. And f of 1.01 is 1.0201 minus 1, and that's divided by 1.01 minus 1. And if you do that out, you get 2.01. Okay, and then lastly, we'll use the closest point on the right-hand side to do f of 1.001 minus f of 1 divided by 1.001 minus 1, and we get 1.00201 minus 1. And if you do this, you get 2.001. So we've got the limits of slopes, from the right and the left. From the left-hand side, we saw that it was 2. From the right-hand side, it looks like it's 2 as well. And remember that if the right-hand limit and the left-hand limit are the same, we can conclude, or at least for now say it seems, that the two-sided limit, okay, the limit as x goes to 1, that limit equals 2. Okay, and that limit has meaning, right? That's actually the slope of the curve x squared at x equals 1, okay, or the slope of the tangent line. And before I move on, I'm just going to show you, for those who are in my class watching, that we actually could do this algebraically at this point because we've done some limits. So we just did a numerical analysis here, and we got, sensibly, it looks like 2 is the answer. But if we actually did this out using algebra, notice that f of x over here is x squared. F of 1 is 1 from the table, divided by x minus 1. But the numerator factors. And once you do that, you can plug in and get 1 plus 1, which is 2. So in any case, the algebraic way is kind of where we're heading, but for now, you can see that conceptually, the limits of the slopes of the secant lines from both sides are approaching 2, so the answer is 2. So certain textbooks and even sections within a textbook might emphasize different things. So I'm just offering here a different definition of the average rate of change. It's really nothing new is happening. It's just that rather than the variable be the actual x value, the b value over here, they made the variable in this notation the distance between the point of interest, which is af of a, and the other point where you're finding the slope. So hopefully you can see just from this diagram that we're still finding the slope of a secant line we're just using different notation, where this time the emphasis is on that h, which is a distance between the two x values. But nothing else changes. And in the next slide, I'm just going to give you kind of an example that you'll find if you do delta math examples, or even other examples in the textbook that use this representation. All right, so this is mainly to help my students who will be doing some delta math problems. This is like one of the modules, and I just want to show how you would do this. So you have a function f of x, and we need to determine the slopes of the secant lines of f for each of the intervals indicated in the table. And it says find the slope of the secant lines of f on the interval 6 to 6 plus h, where h is changing in the table. So just as a recall from the previous slide, we're going to use this definition, right? So the slope of the secant line is going to be f of a plus h minus f of a divided by h. Okay, where in our case the a is a 6. Okay, so I'm going to make a table here over to the side, just so we can kind of keep track of things. Okay, so for instance, well, first we should know what f of 6 is, right? So let's do that. So notice here that my a is a 6, right, according to my according to the format of this. So a is fixed at 6. There are two values that we really care about, right? We really need to know what f of 6 plus h is going to be and f of 6 is going to be in each of these cases. Now, f of a is always just going to be f of 6. F of 6, I plugged it in, and I got out -4. So you might just plug plug 6 in, make sure you get -4. I'm just going to copy that down here, since that's not changing. And then I want my f of a plus h. Okay, that's f of 6 plus h, where my h is changing. So in this case, it's going to be f of 7. And in this case, it's going to be f of 6.1. And in this case, it's going to be f of 6.01. And this is f of 6.001. Okay, so again, why is that? It's because my h is a 1 here, my a is a 6, and if my h is a 1 and my a is a 6, then 6 plus 1 is 7. And if my h is a 0.1 and my a is a 6, then it's f of 6.1. So now I'm going to take, why don't you take a second and evaluate these on your calculator. You can hit pause and then check in with what I write down. All right, so if all went well, you should have gotten that, let me zoom in. You should have gotten that f of 7 is equal to 2. You should have gotten that f of 6.1 is equal to -3.49. You should have gotten that f of 6.01 is -3.9499. And then you should have gotten that f of 6.001 is equal to -3.994999. So you'll notice I'm not rounding, right? Because we want to see the limiting value. So okay, now what? Let's just do what the problem says, which is, if you look over here on the right, it's asking us to find a few average rates of change, or a few slopes of secant lines. And according to this on the right, we want to do this column, so 2 minus negative 4 divided by that, right? F of 6 plus h minus f of 6 over h. Okay, so like I'll do the first one for you, and then I'll pause it, and you can try the rest, and then we'll check in. So 2 minus negative 4 divided by 1 ends up being 6. Okay, now you do the other ones and check in a second. Okay, so here's what I got for the rest of them. I got 5.1, 5.01, and 5.001. So then again, it seems sensible to think if we were to actually ask, or if we were asked what the slope of the secant line is, it seems reasonable to assume, based on the limiting values, that it's probably 5. Okay, so this should hopefully help you with some of those delta math problems that you will come across.